So, presenter view. Perfect. All right. So yesterday we were doing this. Wow, I'm really down. Yesterday we finished off on this slide here. And I find the patterns and trying to figure out an equation or expression that would represent frequency um, for these two types of waves. Now, before I get to that, though, I want to just point your attention to one thing. The first examples that we did were strings that were attached on both ends. And that was very simple. We were talking about like a guitar string or something like that. You can produce different frequencies, and those different frequencies will be the different notes that you play. Um, that concept doesn't apply here. These are not strings anymore. These are now tubes, really, because you have an open end and a closed end. And and I want you guys to try to imagine, if we're still thinking of instruments, what kind of instrument could be represented by a tube that's closed at one end, open at the other, or another instrument that's open at both ends. That's even maybe harder to imagine. Who plays like or has played in an orchestra before? All right, so think of all the instruments that you might even recognize, even those for you that didn't play in an orchestra. There's a lot of them. There's kinds of string instruments and brass instruments and percussion and things like that. And try to imagine what each of these might represent. What could be an example of this? What could be an example of this? Who has an idea?
And the one with the open end could be like a
Could be like a drum. Yeah, absolutely. Um, Now, correct me if I'm wrong, because I'm not a musical person at all. Drums are open at the bottom, I presume. Yeah. Okay, so that works. Yeah. Clarinet. Yeah, exactly. What's the closed end on a clarinet? Which is the open end? Exactly. So you actually close this end with your mouth, and this is the end that's open up. So by that logic, what kind of instruments could fit in this category? Pretty much all the wind instruments, except for one that'll go in this category. Which one wind instrument do you think might go in here? Yeah, that one. What is that one called? Which one? Yeah, a flute. All right. The flutes will go in here because there's like an opening, let's say on this. I'm casting a shadow here. There's an opening like right there where your mouth would go, and it's open on both ends when you're playing it. You're playing air is coming out both ends. That would be a flute or an instrument that has open ends on both ends. It's interesting that we say these things because we're talking about physics, really, and the whole idea of harmonics and standing waves actually is music. It's the reason why those notes sound nice because they fit this thing called a fundamental frequency. Has anyone ever had like a half drank beer and then blown into it and it makes like this resonating sound, right? That doesn't, if you just blow on it regularly, it doesn't work. You have to kind of like modulate how fast you blow into this beer bottle for it to go, and that's because you're hitting a resonant frequency. Have you guys ever seen um, like yeah, though there is some reality to it. Those opera singers will sing and then the glasses start breaking, right? That is a myth because your voice actually isn't that loud and not can't be modulated at the right frequency. But if you have it in front of a speaker, and then this one for sure, there's a Mythbusters episode on it. If you play a specific frequency next to a glass, you'll break that glass. And the reason for that is because you're hitting the resonant frequency. You're causing the glass to vibrate at a frequency that has the biggest amplitude, and that big amplitude is too much for the glass to bear, and the glass will just break, right? And it's not a matter of volume; it's really more of a matter of frequency, and it's quite real. And everything really has a resonant frequency, a frequency at which it starts to hit a standing wave. You can saw those bridges had a resonant frequency. Even you guys have a resonant frequency, though it's much more complicated because you're made up of many different things. If you were made up of just one thing, it could essentially explode you by playing a sound for a certain amount of time. Okay, so that being said, Let's go ahead and get the answers for these. All I want is now, don't tell me how you got the answer. I want to know what your answer is. We're gonna go. We're gonna go do the one on the left first, and I want the expression for wavelength. So what did you guys get for wavelength? For the one on the left. Yeah, Johnny. Exactly. So here the wavelength is 4L over 2N. Oh my goodness. 2N minus 1. Like that. All right. And but if that's the case, can I have an expression for frequency with respect to what we just wrote here? Yeah, then you. Brackets. Yeah. Okay, so I don't mind writing that, but now you have to tell me an expression for the fundamental frequency. Yeah. Yeah. I don't like this class. I feel like I'm getting a show. Okay, can someone tell me for the waves on the right? Can you see from back there, Marianne? Yeah. I know you guys got it because a lot of you left without the answer. So go. Yeah, tell me what it is. Right, perfect. Can someone tell me the equation for the frequency of the nth harmonic? Max? Okay. That. You can also write it as, if you wanted to write it in terms of the fundamental frequency, it would be similar to the other one. Yeah, n times the fundamental frequency, or the frequency of the first harmonic. So far, so good? If you had a hard time trying to derive these, don't worry. I'm not going to ask you to derive it ever. It was more of an exercise of recognizing patterns, and I thought it would be fun for you guys to do that. I really just need to understand how to use them is what's more important. And we're going to do some practice problems. All right, so there's a couple of terms that I want you guys to understand as well. When we did two closed ends, I'm just going to go back here. We talked about the fundamental frequency. And then it was then you have the second harmonic, third harmonic, fourth harmonic, the nth harmonic. Then there's also this other term, overtone. First overtone, second overtone. These are things that I want you guys to be able to apply. Not only in some important terms, there's an important term in music, but they're also going to be important terms when you try to do problems, because sometimes they use those terms in the question, and you have to remember, oh right, the third harmonic is the equivalent of the first overtone of an open-closed tube system. So I'm going to try to describe it over here, and so it's the same two that we just did in the previous slide, and now they have the terms harmonic and overtones. Now this column here, the middle column, is common for both the left and right side, and also common for the two closed end waves. And basically what it is if you're n, if you have some number n, and we don't have a definition for what this n is. I'm going to call this the nth wave, right? If you have the nth wave, then you have the n minus 1 overtone, okay? So there is no overtone for the first of the fundamental frequency or the fundamental wave, right? And then it starts at 1, 2, 3, 4, and it just goes up by that. Okay? So for the overtone, you figure that out by n minus 1. Right? For a closed system, for like a two strings attached on either end, or for a system that's open on both ends, the harmonic number is equal to n. That's different from an open closed because the harmonic number here is equal to 2n. And if you remember, just I'm going to go back to this equation here. The equation is that the frequency of the nth harmonic, right? It's not even of the nth harmonic, of the nth wave, because we can't say that anymore. The frequency of the nth wave is some multiple of the fundamental frequency. So here, because it's 3 times the frequency of the first one, right? Even though it's the next one on the list, it's the second one on the list, so you might think you might have the n of 2, but it's not an n of 2, it's just because it's actually 3 times the frequency of the first one because you can 3 times the wave. So look at that. It's just that's 1/4 of a wave. That's 3/4 of a wave. So that's 3 times more wave or 3 times more frequency if you want to think of it that way. Okay. So let's do some problems. Try to think about this one. So the number of nodes in a standing wave shown in this diagram. Don't have an answer. How many? You said it. I just didn't hear you, and I didn't see who said it. How many? 9. Yeah, exactly. So we count everywhere where there is no movement in the wave. And so for those nodes, there is no movement. Keep that in mind because the lab that we're going to do on Friday, Thursday for you guys, is going to require you to know those terms. Okay, so nodes, antinodes, and things like that. All right. Here's another question. So a guitar string has a mass per unit length of 0.4 grams per meter and a length of 0.8 meters and is placed under a tension of 50 newtons. What is the fundamental frequency of this string? Think about it, do it. If you're sitting with someone, you can discuss it. What's the first step that you guys did? Find the speed. Good. What equation can you use to find the speed? Which variables are important for the speed? We're talking about guitar strings, right? This is a guitar string. We're talking about a string. What's important for the speed? Tension and yeah. So here we go. The equation was V is equal to the square root of tension force over mu, which is the square root of 50 over 0.4. 50 over 0.4 is 0. Yep. You're absolutely right. Yep, it should be kilograms per meter. So let's convert that to kilograms per meter. If it's 0.4 grams, that's very light. 0.4 grams per meter. Doesn't sound right. Let's just change the units of this to kilograms per meter. That way we don't have to convert anything. Good catch, Shani. So what you guys got a speed? 11.2? Everyone agrees? Yes? 11.2 units? Meters per second. Great. So that's the speed of my wave. Now it's pretty much, I'm using an equation for the fundamental frequency. We know that the fundamental frequency, or any frequency, it doesn't really matter. It's going to be the n is going to be equal to 1 because it's closed on both ends. We can say that it is v times 2l over, is that right? I can't remember the equation for this. No, v times n over 2l. V times n over 2l. We have everything, right? We're talking about the fundamental frequency, so our n number is going to be 1. We have our velocity, and our length is given to us. So it's going to be 11.2 meters per second multiplied by 1. All that divided by 2 times the length, which is 0.8 meters. What did you get? 7 hertz? That seems very low. Sure about that? Someone else? Yeah? Okay. 7 hertz. Any questions on that? All right, so the next one. We're talking about a pitch of a note called middle D, and we're referring to this as the first harmonic. And we're talking about vibrating a guitar string, so we know that we have 2 closed ends. The length of the string is 70 centimeters. Calculate the speed of the standing wave in the guitar string. So how would you do that? Go ahead, work on it. Try to figure it out. What's my n value for this? Yeah, it's just 1. We're talking about the first harmonic, or the fundamental frequency, and it's closed on both ends, so we know our n is equal to 1. Now it becomes pretty trivial, right? It's the same equation that we used just before. So the fundamental frequency is equal to velocity n over L. Four is equal to v1 over 2 times 0.7. What did you get for velocity? Someone agrees? Disagrees? Yeah, 411.6. Someone should. When we're talking about the closed close, we agree that that's a string system. We're talking about a wave traveling in the string, so it has some kind of speed. But when you're talking about the open closed tube or the open tube, or forget about that. If we're talking about instruments, wind instruments, what is the speed of the wave that we're talking about? What's the wave that's traveling in the tube? The sound. Okay, so now we have a velocity. We have a typical velocity for a sound. You guys know, who knows what the speed of sound is? Remembers it from maybe one of the earlier slides? Yeah, it's 343 meters per second, roughly at room temperature. It varies greatly actually with temperature. So sometimes when you're going to be solving a problem, they'll tell you the temperature. Most of the time, you can just assume that it's either 340 or 343 meters per second. And if there's a corrective value to make sure, because the temperature is more extreme, then you just apply it. It's like something like X amount of meters per second per degree Celsius away from the equilibrium, which is 340. Okay? So we're going to be doing some problems today where they're going to be telling you the temperature. So just ignore it. It's not necessarily important. Frequency of the first harmonic. They were asking the same things over and over again. I don't feel like you guys need this. Do you want to do these questions or do you want to move on to the next topic? Move on? Okay. All right. All right. Perfect. So let's end this. Open up the next PowerPoint, which is PowerPoint number 5. Yeah. Okay. If you want to find the fundamental frequency, divide it by 5. Yep. That would be the that would be the F1. Yeah. All right. So this one is not a very long PowerPoint because we talked about most of it. It's basically talking about that resonating frequency, the resonant frequency that we're talking about. Have you ever heard the expression, you always sound better in the shower? That's your delusion talking. But there's certain truths to that. The truth is that when you're in the shower, you're in a smaller environment, right? And so your sound waves are actually bouncing off the walls around you, and the walls around you happen to be a multiple of your frequency, of your sound vocal frequency. So you end up hitting a resonant frequency much more easily when you're in a when you're in a very small and closed space. Have you seen anyone here like a professional singer but has done like studio recording of their voice? Huh? Come on, who hasn't done that? Well, if you've in like TV shows or movies or whatever, there's always a person standing in like a glass box, right? And the reason for that is because they're trying to create this idea of a resonant frequency so that you sound better, right? And the sound comes out. So like if you ever compared um, music, like Do you guys still buy albums? Is that still a thing? Let's say you bought an album and you visited them live, the song sounds totally different, right? The one that in the studio sounds very, very clean, and the reason for that is because you're in this box and you're hitting those resonant frequencies much more easily. So it sounds a lot cleaner than if you were to do it in a concert. But that being said, the really good concert halls, they're also engineered and architecturally designed such that it's a multiple of very common sound waves, so that they resonate. It sounds really nice in the whole amphitheater. If you go to Place des Arts and the Wilfrid Peltier, is it Wilfrid Peltier? The main auditorium, not the MS, not the OSM auditorium, but the main like non-MS auditorium. Wilfrid Peltier, is that it? You'll see along the walls that have panels. They gradually grow. It's not like the room is not made like this. The room is not made like this. The room is actually made like this. And the reason for that is because depending on where you sit, you're always going to be hitting, hopefully, some kind of multiple of a resonating frequency in that amphitheater, and you're going to hear the sound a lot better. Now, actually, so what that I will tell you that auditorium, that amphitheater, is actually considered to be a very good one, partly because it's really old, but that the science behind acoustics came about, like, it grew a lot more in the recent past than when this was, compared to when this was built. And if you go into, there's the McGill Faculty of Music, this is where it gets really cool, is that if you're doing an arts degree, you can actually do a whole engineering project with sound. And there's a music, the Faculty of Music, there's a lab that works on the acoustics of instruments, the acoustics of amphitheaters. The whole faculty, the whole department dedicated to this idea. I'm sure other schools too, but I'm just trying to say that like there's like a deep science behind the music that you hear. That's kind of what we're going to be talking about. That's what we talked about at all when we're talking about the anime. Um, and just to connect it back to what we were talking about yesterday with those bridges, those were the resonant frequencies of those bridges. So the wind was blowing at the resonant frequency of the bridge, causing it to have those big oscillations, right? And so you have to, as an engineer, or whatever, a civil engineer, when you're designing those bridges, take into account what the resonant frequency is and make sure that it's not a very common frequency to hit, so that you don't get those big oscillations. You'll get them, but just not, you don't want them to be very common. And then if you do hit them, you want the amplitude to be very low so that it doesn't break the cables or break apart the cement. So we talked about this, like these resonant frequencies in musical instruments, flutes and clarinets, and bottles, a beer bottle. You guys have heard of that? Those people who play the instruments are rotating the fingers in the glass. Notice that each glass is filled up with a different amount of water. So that's so that you can create a different resonant. So you're changing the L in each of the glasses, the length of the tube in each of the glasses, and by rotating your hand, you're creating the frequency, the resonant frequencies of different frequencies, therefore different notes. Okay. Um, when you're playing who plays the trombone? Who has played the trombone? My wife also plays the trombone. Okay. Same thing with her. She played in the in like a youth orchestra, and now she just does it like once every 2 months or something like that. To say that she does it. But in any case, if you know what a which one is it? Can you just imitate what a trombone is? Yeah, okay, it's the one where you move your hand back and forth. Or what you're doing is you're changing the length of the tube, right? You're changing the L, and if you're changing the L, you're changing the frequency at which the sound comes out of it, right? And if you, okay, so now let's go really basic for those of us who've never played music before. You've definitely used a recorder in elementary school. You guys know what I'm talking about? That Yamaha like $10 thing you buy at the pharmacy. You guys know what I'm talking about? Yes, come on. Everyone has played that. And it's the same concept. You block the holes, right? And when you leave the holes open, the sound actually escapes from the nearest hole, right? Or it doesn't escape from the nearest hole, but it's open at the nearest hole. And so the tube length is different than if you were to block that hole and then let it come out of the next hole, right? So you're actually changing the length of the tube every time you block it. Now, if you take up any instrument in between that crappy recorder and it's as sophisticated as like the tuba or the trombone, it's all the same concept of varying the length of the tube and allowing air to escape early or not. Even the saxophone, you press you open and close those valves. Those are valves that you're pressing. And by opening and closing those valves, you're letting air have an escape route or not. And therefore, you're modifying the length of the tube. We talked about all this. This is all the equations that you guys derived yesterday, so there's nothing to talk about here. Same thing here. Questions? Do we need to do these? Let me just see. Speed of a sound wave in the air. They're very similar to the ones we did before, but see now they're starting to measure to mention temperature. Yeah, 37 degrees Celsius. I would not say that the velocity, the speed of sound is at 343. So in this case, they would have to give you the corrective equation. Yeah, pretty straightforward. This is an interesting question. The human ear is an open tube or an open closed tube? What do you guys think? Think about it. Open, closed. Why do you think that?
Because it's obviously open on the first end, and on the other end you have the tampon.
Think deeper than that. The sound goes beyond the tampon. The tampon is really actually just in the middle ear, right? So there's also an inner ear.
But isn't it like blocked the whole? And then the vibration of the tampon moves the other bones.
And then what do the bones do? Okay.
Yeah, okay, right.
And then what did the bones?
Like physically the two stuff.
Okay, so you're talking about the sound. Okay, fine. Okay, so if we're talking about sound, sound will stop at the tampon. Okay, so let's say we're talking about the wave, the oscillation of the wave, whether it's the oscillation of sound or the oscillation of the bones. And what do the bones do? You guys learned this? I don't even. Yeah, exactly. It's a long time. Yeah, so there's three bones in the inner ear called the stapes, malleus, and incus, and these bones are connected together. The last one, the stapes, is actually a plunger, and the plunger is connected to your cochlea. I get it right now. But do you remember? Do you remember with the cochlea? Um, organ or structure inside your ear, and this is filled with a liquid. And the stapes, once it's vibrating, you plug in the liquid in that. Actually, imagine you have a closed tube, it's not necessarily closed, but imagine you have a closed tube and you have a plunger at the top of one end of it, and you're just plunging up and down, then the liquid inside will move up and down. And along the walls of the cochlea, there are these things called hair cells or voltage activated um, neurons that when you plunge, the hair goes downwards and it opens up the channels and allows ions to flow in, and it sends and that initiates an action potential to send it to your brain. Any of this ringing any bell? No? I mean, it's okay. I mean, it's not bioclass, but that's basically how it works. However, there is you guys remember the round window and the oval window? Does that ring a bell? Maybe for some of you. It's been a long time. Let's just say, I don't know if you guys remember from like Sec 3, but essentially there's an opening at the other end. So what happens is you have your and it makes these bones if these the plunges in and out of the window. The oval window is the opening between the safeties and the and then you move the plunge in and out. And then look, it rotates, it goes around the end and comes all the way back, and then comes out. The pressure is released by the round window. Right, so from the oval window to the round window, and then you have this It's probably safety where you can equalize the pressure. You know, when you're like when you yawn, you feel this is connected to your throat. So the pressure comes in this way. And what's that open to? If you want to think of it. If you're going by your right, it could be a nothing. If you stop that, the sound is on. That was a big tangent, but okay. I would like you guys to do this question and then we're going to move on because I think you guys know this stuff pretty well. Do this question. It's like the last like tough question, I guess, for this unit. And if you guys are comfortable with it, we can go to the next subject. Sound good? Go. Let's just say fine. Tough question. Take your time. We're actually back on schedule, so we've essentially nullified that one class that we missed. If we ever do get it back, we'll just call that class the rest class. What did you guys do as your first step? Draw it. Good. Which one did you draw? The pendulum or the pulley? Did you do both? Okay. So you have to draw the pulley version. Let me erase this CD. If you have to draw the pulley version, it was horizontal, right? Then it would fall off some midway point like this. And then here you have the mast, and this is attached to something. So why was it a smart idea to try this? You can write down the numbers for sure. Well, yeah, well, we don't know the gravitational acceleration force or acceleration. We know that if we drew a free body diagram, physics, we draw a free body diagram. Whenever you have the opportunity to do that, you draw a free body diagram. So there's a force in that direction. And this force, we're going to call it mg because it's the force of gravity, right, pulling it down. It's not our g, it's not 9.8, but it's a g. And so if there is a force pulling it in that direction, that means there's a tension pulling it in the upwards direction, right? Because it's not moving anywhere. And if this pulley is of anything to show, that means that there's going to be a tension here as well. And this tension are going to be equal, right? In fact, if I wanted to be even more precise, I can say that there's a tension here and a tension here. A pulley, what it does, if you guys remember from mechanics, a pulley, all it does is just change the direction of forces. It doesn't add any forces, doesn't take away any forces. Of course, we're talking about a perfect pulley, but in essence, the pulley just changes the direction. Now we have the tension here, right? And we have some length, which is, that's going to be, that length plus this length is going to be the length of the whole wire. We're going to need to know that for later. And the point of having the tension is excellent because now we can talk about the velocity of the weight. Okay, so based on that, continue trying to work on it. You guys are too quiet again. Gotta find something with you guys. I don't know what it is. It's like you don't need to whisper, just talk normally. It'll encourage others to talk. What's that? But if other people talk, no one would hear you. I understand what you're saying. But if so everyone else, please talk so that no one feels self-conscious about talking too loud. What if I played music? Would that help? A good song. What's a good, like, let's solve this physics problem song? Since we're doing orchestra. Yeah. Good question. I think you can ignore it. It's light enough. It's 1 gram per meter. If you're into classical music, this is a really popular one that's quite good. My speakers are going to suck, but it'll break the silence, hopefully. kind of worse.
Yeah.
Watch out.
If the
Did
frequency,
you take the L out of the square root?
no, it never was because the second harmonic, so it's 2B over 2. So that if they both cancel off, then you have V over L and you have the equation for L. So you will just solve it. Because you're only representing L. So then you know V. So I just substitute everything for V because you have the split, but you're missing V. You have the max.
Oh, I see. I got it.
So then it's this, and I plug it back
Okay, sounds all right. The process is good. Once you get it matching,
and just
I did it a way different way, but it's the same thing, I think. Did you use this at all?
oh yeah. Yeah. I just use it for
Yeah. I don't see a problem. Good part, no question, but there's two parts to it. They're not two parts, but there's two sections of it. It's the two big steps in Yeah. Yeah. Just the wire is one thing. That's the mass length density of just the wire. And aside from the wire, you also have like a mass that you can hang from the wire. That weighs 1.25 kilograms. Well, you convert it into kilograms. So 0.001. So here you have, so your equation in character is correct. Okay. And this value here is 0.0001. And now right here, that's your velocity. Not having this is the second harmonic. Equal to the velocity given by this multiplied by m, which means 2 to the second harmonic, divided by 2f. This is 2 then. Oh, right. So if you look at it, the vibration is cos n cos n. And this is not, you wouldn't consider this part of the oscillation. Exactly. Okay. All right, let's try to solve this together and see where we get. So we need to draw something first. And what we're going to draw is this system here. And like I said, there's going to be a tension here, a tension here. And if the whole length of the wire is little l, right? The whole wire is little l. We can consider that this top part only, the part that's vibrating, right, with the second harmonic frequency, we can call that capital L, and that's half of the little l. And okay. If this is going to be big L, and it says in the question that you put the pendulum, so that you put the pulley here, such that this is half of, not half, like, the pulley is exactly halfway through the wire. So you can say that L is equal to, or big L is equal to little l over 2. And little l is going to be the length of the whole wire, and big L is just the part that's going to be vibrating in the frequency that you're talking about here. So let's write down our equation for velocity, or not velocity, rather frequency. And the frequency of the second harmonic, which is what they give you in this question, is equal to the velocity of the wave, which we have to figure out, we don't know anything about, multiplied by n. In this case, n is equal to what? Because it's the second harmonic, divided by 2l. All right, this is the equation for the nth harmonic, is the one that we derived yesterday. So I'm going to rewrite this as, so the frequency that they give you is 100. That's equal to v, and we know that v is equal to the square root of tension force over the mass length density, mu. Okay? And the tension here is going to be equal and opposite to the tension that's being pulled. So this is pulling at it with some force, and that force is what's going to be equal to the tension in the wire over here. So that would be just mg, right? Because the only force pulling it down is the mass times the gravity of this special planet. So we can say that v is equal to the square root of mg, and g is what we're solving, is the ultimate question here, divided by v. So I'm going to replace that in our equation at the bottom here. So I have the square root of m is 1.25 g over mu, which is 0.001. That's our v. Multiplied by 2, because that's our n. All that divided by 2 times L, and our L is, our big L is actually just little l divided by 2, so I'm going to put little l divided by 2. And I'm just using this as foresight because I know that later on, I'm going to need to use the whole length of the wire when I'm talking about the pendulum, because it says that there's a second experiment that the person did with the pendulum, right? So now I can just simplify some things. I have this, I can cancel out my 2's, and I'm going to have an expression where I don't know L and I don't know G. And that's fine because I'm going to have another equation later on. So now it's going to be 100 times the square root of 0.001 divided by 2 times the square root of what am I doing here? 1.25 equal to G, or rather the square root of G over. So far so good? Can someone find me a number for this? For what I wrote down here? 0.141? 1.4? Okay, so I need a third person to 1.4, 1.4, okay, so let's go with 1.4. Just 1.4 straight up, or, okay. I'm not going to give it any units because it's the square root of G over L doesn't really mean anything. All right, so that's what that ratio is, and I'm going to rewrite this ratio as G is going to be equal to 1.41 squared times L squared times L squared. We're trying to solve for G actually, so I'm going to do it the other way around. Sorry, I'm going to solve for G instead, so I'm going to put, that should be this, square root of G over 1.41 is equal to L. Okay? That's going to be my first equation, 2 unknown. It also says that you do the same experiment with a pendulum. If you're doing the same experiment with a pendulum, then, and you have a period there, that really works well. So he says, you find that the pendulum requires 314 seconds to complete 100 oscillations. So how long does it take to do one oscillation? Let me see if I did that right. 314 seconds to do 100 oscillations. Why don't you just divide it by 100? Am I doing this wrong? But they're doing 1 over, they're doing 100 divided by 314, which gives you 0.318. Yeah, that's what I'm trying to say. Okay, so let's try to do this real quick. So that would be, yeah, I could use both, but you need to know which one you're using. Otherwise, it doesn't work. So, so 314 seconds for 100 oscillations equal to 1 second. So how many for 100 seconds? Did I do that right? Nope. So what would this value be? This would be 3.14, and this would be equal to 3.14 would be the period, right? Because that's the number of seconds per oscillation. Is that what you guys did? You found the frequency. Okay, I thought you were using the term of the period. Okay, so let's equal the period. Okay, perfect. And we know that a period of a pendulum is equal to 2 pi square root of L over G. That's one of the equations that we derived like 2 classes ago, I guess. And so now it's simple because I have a value for t. It's 3.14 seconds. And I have these two equations. This would be equation 1, equation 2. And I have two equations of 2 unknowns. Simple enough at that point after that? Did I confuse anyone? It's okay if I did, I just have to re-explain. Okay, I'm assuming that everyone at least understood how to do it. Doesn't matter if you get to the right answer because you made some calculation mistake, as long as you understand the physics behind it. Sure, go ahead. I can't do this in my head, so it might take me a few minutes to do it. So I'm gonna put the L into there. I might need some more space. No, but that's why I have this equation up here, remember? So now, okay, so I'm going to say that 3.14 is equal to 2 pi times square root of the square root of G over 1.41, all that over. How the heck do you solve this? Square both sides? Maybe times. You guys are doing this or you're watching me do it? I hope you're not watching me do it. Try doing it on your own, because I don't even know if I'm doing it right. Square root of g over 1.41 over equal to 4 pi squared g to the 3 halves to the 3 4 squared. That's what g is equal to. I got 0.498. Let me know if you guys get the same thing. I definitely could have made a mistake, but that's what I got. You got double that, right? You got the same thing? I'll give you guys a chance to catch up on that algebra. Good? Any questions? Shani, let's see. Where, up until where did you have the same thing as me? Okay. Maybe you want to write it down and maybe think about it a little bit later. If you have a hard time with this, because this is a lot of algebra to be done here, come and see me. I'll gladly do it with you. Because I feel like at this point, half the class understands it, and the other half is just like, oh, you lost me out. There's a captain of the scientific team. Yeah, Amanda? Which, the big L or the small L? So before I talked about the pendulum, right, I was solving for, I was going around here. This part, you followed me? I replaced the big L with the small L. Small L divided by 2 big L. And I isolated G over L because those were my two unknowns. And I picked one of the two variables to like substitute. I chose to substitute out from here. I isolated little L, right? So that I can now, everywhere that there is this little L, I can rewrite this instead of it. Okay, so I know that the equation, or is it the equation? The equation for the period of a pendulum is 2 pi times the square root of L over G. Now, instead of writing little L there, I substituted it by this expression, right? And it was weird because I got a square root instead of a square root, and that might confuse you with the algebra a little bit. And so based on that, now I just have one equation and one unknown. My only unknown is G. So I just did algebra to solve for it. Yeah. From here to here, okay? Okay, so the square root of G divided by G, I can add the exponents up together because it's like multiply. So it's like the square root of G multiplied by G. That's how I got the G to the power of 3i. Because it's divided by. You know what I'm saying? So if let's say I had 10 divided by 110, exactly, so I take this and then multiply by the top one. That's what I did here. So it's the square root of G divided by 1.41 divided by G. So I brought the G and I multiplied it. Or division, so it doesn't matter. Yeah. I brought that back up. I squared this, and that's how I got my 4 pi squared. So I put my I didn't follow what you said at all. Yeah. That should be down. Yeah. That one is down already. So what? How would you? Okay, let's say you did that. What would you do next? Okay. Oh, I see. Let's see what you did. You might be right, actually. Let's try doing it that way. What answer would you get if you continue solving it that way? 8 point something. You might be right. Yeah, Leo?
Yeah, the thing is that when you divide by a fraction,
Yeah.
it's like multiplying by the inverse.
Right, but what she's saying is, and I understand her what she's saying now, she's saying that it's the same thing, if I do the square root of g over 1.41, multiplied by 1 over g. So then it would be the square root of g over 1.41 g.
Yeah, but isn't it just like the square root of g divided by 1.41 over g? So then you multiply by the inverse.
I see what both of you are saying. Let me try to think about which one's the correct. There's obviously one correct way of doing it. So this should be in brackets because that's L, right? That's L right there. So that's L. So you have to divide it by G. Dividing it by G is multiplying it by 1 over G. So I think China would be right. Did I convince you there? So this is the equivalent of the square root of G over 1.41. All of that over G. This and this are the same. Yeah. So then that would have to be it. Right? So then it would be 1 over 1.41 square root of G. Right? So let's solve it now and see what we get. Thank you, Shani. It's not the most simple algebra, to be sure. Let me just erase it here so that we have the right answer. So it's going to be 1 over 1.41 square root of g. Now let's solve it. So 8.06. Tanya, is that what you got? No. Who needs official answer? 8.06, not 0.08. Okay. I'm okay with that answer. Sounds good. The lab that you guys are going to do on Thursday is actually basically this lab here, this part of the lab. You're going to have a machine here that's going to vibrate the string up and down, and you're going to hang different masses from this to create different tensions. And the different tensions are going to make it so that at a fixed oscillation frequency, you're going to get different harmonics here, different multiples of a fundamental frequency. It's pretty straightforward. It's going to be really loud because those machines that vibrated are enormously loud. Can I move on from this? All right. Let's take a 10-minute break, come back. We'll do one more small thing, and then we'll call it a day. Come back at 12. Until 12:30, right? Okay. Double make sure this is okay. The Van de Graaff? Like the big ball you're talking about? Oh, yeah. $100, that's it? Now, is that expensive or not expensive? Because all you're doing is pointing it at things and then. Yeah, I guess it's kind of expensive. Why did you look that up? Were you afraid that you broke one? No. Have you done E&M before? You did it two years ago or 2 sessions? How did you find it? Was it this course? Which one? Oh, okay. There is someone though they're doing like they're like 21 years old or something like that. Yeah. And there's no shame in failing a course. It takes a lot of resilience to have to keep going, you know? Yeah, it's this is considered a pre-university CJEP. So you'll see only like straight out of high school, a couple of years, and that's it. Dawson is one of those. Is it bigger than all the French ones? Okay. And there's also adult education there too, right? What is it called? Oh, that's a cool. If you can cruise the world, why would you want to cruise the St. Lawrence River? You guys ever see a show called The Deadliest Catch? It's a documentary on fishermen, crab fishermen, I think, or just fishermen in general. Crab fishermen. Oh my God, that sounds scary. The whole thing is. I can't believe that there's a job that people. Yeah, but I mean, what else? How would you make that more safe other than being on a boat? Yeah, cost more money though. Then your crab would cost a fortune. That show scared me from anytime I think about going on a boat. I think of that show, and I'm just like, nope, not for me. The answer, I double checked it, is 8.06. We're good. Official answer. There you go. How's that? Now it's official. Okay. Anyone listen to classical music just like that for their own pleasure? It's good. It's very good focusing music. Hmm. Do you guys feel like doing more notes, or do you want to do a virtual lab? Are you tired of notes? Tired of notes? Lab? So let's do a lab. Yeah. It's a virtual lab. It's not a real lab, but yeah, kind of like the one that we did the other day. Like the string. It's the same group that made it. But this one you guys don't have to download. You have to make sure your Java is up to date. So it might not work on every single computer. Yeah. So at the end of 6. Or you can just actually you need to download the file anyway, so you can go to Moodle and download. I think it's lab 6. Yeah, this one you have to download. What symbol is that on your computer? Is that Hogwarts? That's so cool. Where did you get that? You didn't even work with someone who doesn't. But the thing is, there's so many Macs. inside of that. But you need to be able to do these because there's a lot of them in the year. Can you guys try downloading it now and try updating your Java? It's the Ripple tank. What number is that? 6? Oh, weird. Try the latest one, so 6. So what is the error that you get in when you try to open it? Can't be open because it's from an unidentified developer? Exactly word for word? Okay, let's see what it says to do here. Download the jar file for each SIM you would like to use. In Finder, right control, click on the icon of the SIM, select open from the top of the contextual menu that appears. Click open in the dialog box. If prompted, enter administrator name. Can you try that? So it says in Finder, right click the icon on the SIM or control click the icon on the SIM. Select open from the top of the contextual menu that appears. And then it says click open in the dialog box. If prompted, enter an administrator password. That's for Mac. Anything?
Yeah, it works. But then you need to download another Java.
Let me see what you mean. That's what we're doing a lot of these simulations. Yeah. This one. For this, the problem which you did? What answer did you get? That's okay. I got 8.03 or 06. Close enough.
Oh, Java's downloading.
Okay. All right, so here's what we're going to do. Those of you who are with Macs, try to pair up with someone who's got a PC for now. And Leo and I are going to try to optimize it so that Macs work. You guys are going to go to Moodle, download the last lab. I think it's called 6 Ripple Tank, virtual Ripple Tank. And please work on that for the rest of the period. The what do you call it, the instructions are in that document that you're going to be downloading, as well as the link. Yeah, Shani. I might have just uploaded it twice. I think it's the same thing. I want to see if it works. So pair up with someone who's got a Windows computer. There are many of you. Good. So Valerie's got one. Fred's got one. Amanda doesn't have one. Laura has one. You can be in groups of 3 if there aren't enough. Yeah, you're gonna need to update it. also install mechanical issues, that locks up. When you're starting to install, let me know. We're gonna pass the furniture. Because I'm not sure. You will need it eventually, so if you guys work on yours now, you might need it later. It works. Oh, actually, you don't use Edge anymore, right? I'll verify. It works. Works perfectly? And the army does plug in or go around and show people. Sure, yeah. Yeah, yeah. It does require using Macs, but thank you. Yeah, I see the shut on the program. And the download file. Oh, wow. But there's so not only the why that is not perfect. Did you show the new Leo? What about a dam oscillation? We wanted a dam oscillation. Unless, like, Earth moved to the same oscillation. When you go back to the slides, on top. When you're looking at that, other reasons that's never changed. say I travel here. No, the only way that's possible is not change it. You go have it. Yeah, we're not doing all this. How far you live? I used to do, I did my master's in job. One time I missed the class and I had to. That's why I got started. No, just that. Just that, so maybe. Maybe actually right after.